Good evening. This is our semester project for CS 4362 hardware description languages. In this project, we have created a pipelined MIPS processor. So to demonstrate the simple pipeline processor designs, we have used a MIPS or a MIPS processor in our project. So typically, MIPS processor has 32 registers, and the first register is hard coded to the value 0. And starting from that, we will have a few different registers, we name them as 0, 1 up to 31. So in a basic MIPS processor, there are few types of operations that can be done. Simple few of them are arithmetic operations, register to register. As an example, this addition operator, we add two operators and save it in the register destination, and also immediate value and unsigned value. And there are other types of operations like memory accessing and branching. So for the memory accessing, we can either load a value from the memory, LW operation, or save a value to the memory, SW operation. And also in the branching, there are typically two types of operations. One is the conditional jumps, simply branch not equal jump or branch equal jump, or the unconditional jump, the just jump, and also the another operation that's not mentioned in here, jump to register operation. So this is our project, which consists of 33 modules in 33 source files, and also tested in 36 test bench files. So if I give a basic introduction to the 5-stage instruction execution in a MIPS pipeline processor, these 5 stages are fetch, decode, ALU operations, memory access, and results writing. So if we consider the add operation, first we read instruction. That means we are loading the program counter to the respective value. Then we decode the instruction. Since this is an AND operation, we will take the first parameter as the operand 1 and the second parameter register as the operand 2. In the ALU part, what happened is the calculation or the addition as in this operation. And since this instruction does not have any memory access, we have left that instruction, that memory access part from this operation. And also at the end, we will write the result to the third register. If we consider the load word instruction, first the same as the before instruction, we load the value instruction to the program counter, then take the first value as the operand 1, and then what we have, the value, the immediate value 20 as the operand 2. But in here we have to do an arithmetic operation to identify the exact memory location from the given instruction. So as in here, to calculate the correct value, we have to add 20 to the value in $1 or the register 1. So after that, we will do a memory address operation to get the value from the memory, and then we store that value in the register 3, same as in the branch equal operation. So this is a typical single cycle implementation of a memory of a MIPS processor. So it will have registers, multiplexers, also instruction memory, which hold all the values, instructions in the processor, and also arithmetic and logic unit, and also data memory, which stores the values of the calculated instruction. So if we consider a multi-cycle implementation, we will divide each section to the different stages of the execution. It can be instruction fetch, which use the instruction memory and also the program counter. Then instruction decode, which has the registers, and also in the execute the ALU section, and also the memory access, the data memory, and also accessing the RAM, and at the end write back, which writes the values back to the registers. So the first unit that we are covering here is the control unit, or the heart of the processor. So this control unit is responsible for managing the all 6 instructions that we are going to implement. So if we go to the control unit, the control unit is capable of handling these type of operations, the R type operations or the register type operations, the load value, store value, branch not equal, and also the XOR immediate value, jump operation, or default value for other instructions. If I go through these instructions, the register type instructions, we have, if when we are doing operation in register value, we have to do register destination and also register writing. And also we have the ALU operation 10, which will be discussed in future by Ihan. In the load word instructions, we will use ALU source to calculate the address, and also mem2rec to storing the value from memory to register, and also memread operation to read values from the memory. In the store operations, we does not care about the destination, and we also need arithmetic operation to calculate the immediate address, the exact address of the exact address of the value, and also we need to enable the memory write command. In branch not equal operation, we will have to do a branch operation. And in the XOR operation, we have to do arithmetic an operation to perform the XOR operation, and also register writing to write back the result. In the jump operation, we will not require to do any operations related to register writing, arithmetic operations, memory operation, or any other operation, but only to do the jump operation. So this gives the control unit. Next, we will start from a very basic implementation of flip-flop. So the flip-flop is used to keep the values for further processing, or to keep a value stored for past executions. The register 32-bit is implemented using flip-flops in an array. So what happened here is like we take the value register data as a logic vector and store it in our system. To write the value, we have to enable the write enable, and to get the value out, we will use the record. So this rec bit is the implementation of the flip-flop operation, and the register 32-bit is implemented using 32 flip-flop modules. The next what we have is the register file. So the register file represents all the registered in our system. So we are capable of reading two registers at the same time. We have to mention since a MIPS processor has 32 register values, we are using we require only 5 addresses to identify the each register separately, and also to write operate value to write to a register, we can use the write register, and also to pass the value to the register file, we can use the write data pins. And also we have to enable the read write operation. We have to enable read write to write to the value, and from the read data 1 and read data 2 we can get the values outside from the module. So this register file is implemented using 5 to 32 decoder, RAM, and also using a 32 times 32 to 32 multiplexer. So what happened here is like when we want to write to write to a register, what we do is this represents a single register value having 32 bit value. First, when we want to write to a value, what we do is we pass in the write data value using these pins, and we choose the address of the register value using the write register implementation. So what happened here is it passes 5 input values to the decoder and enable one of these values. So this write data value will be written to that register. So if you consider this as to be the first register and last one as to be the second register. So if you want to write to the second register, what we have to do is we have to pass 0001 for it will enable this register, so we can write the value to this register. When we want to read a value, what we have to do is to pass just the read value read register address to this parameter, to this multiplexer. So it will get the value from this array module and pass it to read data 1. We have named this multiplexer is 30x times 30x because this one value has 32 bits and we have 32 of them, and the output value is again 32 bit. So this is the register file of this is the implementation of our register file. So we have a decoder, register array defined in ROM type, and also a multiplexer 32 times 32 to 32, a multiplexer to reading the values. And also we have hard coded the 0 for the 0th or the first register. Next, what we have is the data memory. So data memory is what keeps the values of the data, which is the result of ALU operations. So for this module, we have 4 inputs: address, write enable pin, write data pin, and also clock. The output of this module is data out pins, which is 32 bit. So inside the data memory, for the constraint of basis 3 board, what we have done is like, even though data element is 32 bits long, we have divided them up to 8-bit 8-bit section blocks. So in the data memory, we store the values in, instead of 32-bit blocks, we store them in 4 different 8-bit blocks. So when you want to write to a new address, when we want to write to a new address, what we have to do is input the address value and also the write data value. So it will be divided into 4 sections, and starting from the address mentioned in the address block and address pin, we will write to the consecutive 8 block memories. When you want when for reading, what we do is when the address is mentioned, we will concatenate the consecutive memory blocks starting from the address, and then we will return it out to the data module. So this is the implementation of the data memory. As you can see, first we will, when write enable is 1, we will divide the write data mode, write data 32-bit vector into 4 different 8-bit vectors, and we will write them to the data memory. When it's asked to read the value, we will concatenate all those values and create a 32-bit output value, and it will be written. The instruction memory is the part of the MIPS processor that hold all the instructions to be executed. When the program counter mentions the address, it will return the corresponding data value in the instruction memory. Since this instruction memory, for simplicity, we have implemented in a read-only memory. So the values in the module in the instruction memory cannot be changed. When the address is mentioned, we will output the respective STD logical vector to the out. So this is the instruction memory. These are the instructions that are ready to be executed in our MIPS processor. And when reading the value, when the address is given, we will get the corresponding value from the ROM and output it to the data output. Starting from here, the zero extension module, Vihan will explain the next part of the presentation.
Thank you, Targa. So I'll take from here. So in the zero extension module, what happens is, so we receive a signal of a length of 32 bits. And in the zero extension, what we do is we append zeros, 16 zeros in front of the received number and output it as a 32-bit long number. And in the sign extension module, what happens is we receive a 16-bit number, and what we do is we take the first means the 15th bit of the received number and copy it for so we copy the 15th bit number for 16 times and add it to the front of the received number and output it as a 32-bit long number. And in the shift left to module, what happens is we receive, let's say, we receive a 32-bit long number, and what we do is we basically shift the number left by 2 and add 2 zeros at the end of the number as shown in the presentation. So if we look at the code of these three modules, so in the serial extended module, as I said, 16 zeros are added in front of the received number, and in the sign extended module, what I do is we copy the 15th bit of the received number and append it 16 times in front of the 15 times in front of the received number. And in the shift left to module, so in the shift left to module, what we do is we copy the numbers from first at first 30 bits of the number and append 2 zeros at the end of the number and make it shift left by 2 bits. So let's go back to the presentation. So next we have 2 into 32 to 32 marks. So what happens is we get two buses with the length of 32 bits. So what from a select we choose one from these buses and output the selected bus from the multiplexer. So, and then we have the 3 into 32 into 32 multiplexer. So in this multiplexer, we receive 3 buses from the, so as the input. So for the select, we have select of length 2 to choose one of these buses, and this outputs the selected 32-bit mux. So this 3 into 32 into 32 mux is built using 2 into 32 into 32 mux, which I'll be explaining the code. Let's look at the code of these two modules. So let's look at the 2 into 32 to 32 multiplexer. So this is build up using 32 2 into 1 multiplexers. So we receive a box of 2 buses of 32 bit of length, and we assign each bit for each 2 into 1 multiplexer. And from the select, we pass the same select to all the multiplexers and get the relevant bus as the output. Then let's go to the forwarding mux, or the 3 into 32 into 32 mux. So this is built using 2 into 32 into 32 mux. So we receive 3 buses of 32-bit length, and we assign first 2 buses, or the A and B buses, to 2 into 32 into 32 mux, and then we assign A and C buses into the other 32 into 2 into 32 into 32 into mux. And according to a select first bit, or the bit at the index 1, we select one bus from each 2 into 2 into 32 2 into 32 into 32 mass, and out and input those 2 inputs to another 2 into 32 into 32 marks, and using the second bit of the ALU select, we get the desired result, or the desired bus as the output from the 3 into 32 into 32 into bus. So let's go back to the presentation. So let's look at a simple 1-bit adder, which we'll be using to build a 32-bit adder later. So this is like a normal 1-bit adder, normal 1-bit adder, which is like to add 2 bits. So we receive two bits as A and B. So sum is received at and the carry in as well. So sum is calculated from A XORing the XOR by XORing all the 3 inputs, and the carry out is calculated by A and B, or carry in and A or B. So if either both bits are 1, or either carry in and or either any A or bit is 1, the carry output will be 1. and the sum is output from sum, and the carry out is output from the 1-bit adder. So let's move to 32-bit adder. The presentation 32-bit adder. So for in the 32-bit adder, it is built up using 32 1-bit adders. So we receive 2 buses of 32-bit length, and each bit is assigned for a 1-bit adder. And the carry for the first adder, we input the carry in as 0, and there onwards we input the carry out of the previous adder to the carry adder next to it. So it's act like a ripple carry adder in this scenario. So let's look at the code that is relevant for the 32-bit adder. So 32-bit adder is made up of like I said, it is made up of 32 1-bit adders, and we receive AB as 32-bit long in buses, and in the this is the ALU adder 31-bit. So let's look at the code of the adder 32-bit. So we receive 2 buses of length 32 bits, and then we declare adders 32 adders. So for the first adder, we input carry in as 0, and there onwards the carry of the previous adder is fetched to the so the 2 bits are assigned to the A and B bits of the 1-bit adder, and the for the first adder the carry in is set as 1 bit 0, and then then there onwards the output of the previous adder is fetched to the carry in of the next adder. So let's go back to the presentation. So let's move into the arithmetic and logic unit of the processor. So let's first look at 1-bit ALU, where later these 1-bit ALU are used to build a 32-bit long ALU. So in the 1-bit ALU, we receive input as A, B, 2 bits, and ALU control, and less indicating whether the number is less than bit called less. And so inside the ALU, there are 3 2-into-1 multiplexers. So in the first multiplexer, we compute the add and subtraction of the 2 bits we received, and input them as the input for the 2-into-1 multiplexer. And in the other multiplexer, we calculate the XOR and the less bit as the input for the second multiplexer. And according to the ALU control signal we receive, and using the first bit of the ALU control, we decide which is to choose from these 2 multiplexers. Like if it is 0, the first multiplexer will output the add, and the second multiplexer will output XOR. And if it is 1, the first multiplexer will output the subtracted result, and the second multiplexer will output the less bit, indicating whether the number is less than or equal to each other. So in the next multiplexer, there is 2 results that was output from the previous 2 multiplexers is fed as inputs, and using the 0th bit of the ALU control, we decide which result we want to get as the output of the ALU. So if it is 0, it will output the result we got from the add and sub multiplexer. If it is 1, it will output either XOR or less result. So let's go to the code of the ALU 1 bit. So 2 bits are received as AB and bit indicating the less than, and the ALU control is received as inputs. And then we have a 2 to 1 two multiplexers. So one is the inputs are the input bits, and then using ALU control, we the ALU submodule is a module which computes the addition and subtraction of the 2 bits we provide, and the output is given to the so this is the multiplexer that is calculating addition and subtraction, and the output is given to the add sub signal called add sub out. And in the next multiplexer, the XOR of the 2 bits and the less signal is given as the inputs, and the ALU control first bit is given as the select, and the result is stored in the XOR less out signal. And in the next multiplexer, we give the result from the add sub out add sub unit and the XOR as the inputs, and using the result of the ALU control 0th bit, we get the desired result from the ALU 1 bit unit. So let's go back to the presentation. So the 32-bit ALU is made up of like a collection of these single bit ALUs, and according to the ALU result we provide the same ALU for all the 1 bit ALUs and get the desired output from the output signal. And if there's addition, if there's a carry out will be output from the carry out as a signal. And if there's overflow when we are doing calculation, the overflow bus will indicate that. And if it's a negative number, if the result is a negative number, negative flag will get high, and another flag to indicate the 0 value is also there in the 32-bit ALU. So let's move to the next component. So next we have the ALU control unit, where we decide what ALU operation should be carried out according to the instruction that we have received. So in the instruction decode process, we divide instruction into two several parts. So 2 of them is ALU OPO, the ALU operation part, and the function part. So according to the combination of these 2 values, the what ALU operation should be carried out is mapped according to the table shown below. So if the ALU operation is 1 and we don't care about the function bits, it's the ALU control should be 1. That means the XOR operation should be carried out. And if the ALU operation is 0, we don't care about the function bits again. The ALU control should operate add operation which is relevant to the load or store instruction. Then if the ALU operation is 0 and 1, the function bits are not yet again considered. The ALU control should be 1 and 0, and the subtraction operation should be carried out. And branch not this is the operation that should be carried out for a branch if not equal instruction. And if the ALU operation is 1 0 and also the function value is 1 and 5 zeros, the ALU control should perform adding operation, which is relevant for the a normal add instruction, adding 2 values into registers. And if the ALU operation is 1 0 and the function is 1 3 zeros 1 0, the ALU control should perform a subtraction operation, which is indicated by the 1 0 of the ALU control. So that is relevant for the subtraction of 2 values into registers. And then last we have when ALU op is equal to 1 0 and function should to be equal to 1 0 1 0 1 0. The ALU should perform a set on less than operation which is relevant for the set on less than instruction which sets a flag if the value is less than if it will compare two values and it will set if the value in the first register is less than the value in the second register. So these ALU control bits are set according to the multiplexer outputs that was described in the previous ALU 1-bit operation. So if you can remember the 0 1 means like if we go back to the 1-bit ALU, the 0 let's go back to the 1-bit ALU. So 0 1 means the addition is selected from the first multiplexer and the XOR is selected from the second multiplexer, and 0 and 1 from the second multiplexer using the 1-bit, it will select the XOR operation. So that's how this ALU works and how ALU control unit integrate to this. So let's go back to the next component. So next we have another instruction which is a jump register instruction, and so this is like the control unit that decides whether that detects the jump instruction and emits the jump control signal if a jump instruction is in the program. So the combination of the ALU operation and the function unit is 1 0 and 0 0 1 0 0 0. So this combination was not there in the previous ALU operation unit. So this was not handled in that occasion. So this is in the previous occasion, all the other combinations that was not in that table was like the operation for those is as the default value it is set to 0 0 ALU operation. So in this case, if the ALU operation is 1 1 0 and the function is 0 0 1 0 0 0, it will detect from the JR control unit and emit the JR control signal, resulting in a jump register instruction. So if you go to the next component, so this is a unit that is made to along with to handle control results if there's a branch instruction or a branch instruction or a jump instruction. Some instruction should be discarded without executing from if the result of the jump or branch if not equal instruction is not the expected one. So according to the input received from as the signal received as jump branch not equal or jump register, the instruction, the ID flash or the instructions in the instruction decode phase is get flushed, or instruction in the fetch phase is get flushed. So the instruction decode flush is high only when if the jump and the branch not equal signals are there. If the instruction fetch phase instruction are flushed when all the jump branch not equal and jump register signals are there. So let's move to the next component. So this is normal processor. From here, I will hand over the presentation to Tarek to continue.
Thank you, Rehan. So in here, what I have shown here is like the normal pipeline of a processor. So we have implemented these components individually, the instruction loading, the memory operations, then the arithmetic and logic unit, and also then storing the memory back, and also writing back the results. So this is the normal pipeline version of a processor. So if you consider a normal single cycle processor, what happens is like a normal load operation, which require the memory to access can be will implement in less time than the store operation. So there will be a waste if we have to go with the single cycle implementation of a processor. So to increase the throughput of the system, what we can do is to pipeline the operation, that for each this load operation, we will divide it into the previously discussed 5 stages. So as you can see, the load operation has all these five stages, but only the store has only 4 of them. So uh, it it is the ways to go with a single cycle implementation. What we can do here is like to pipeline these operations, because different part of the processors are involved in these different sections. So in the instruction fetching, the instruction memory is used. In the instruction decode the unit, the decoder, and also the instruction fetching can be used. And here the ALU instruction decoding, instruction fetching, all 3 modules can be used. So we can use more modules at same time and increase the throughput of our overall system. So when implementing these systems in pipeline structure, we will have to face 3 hazards. So the first one is the structural, the data, and the control. So in the structural hazard usually occur when we are using two instructions are using the same hardware resource. So the data hazard is occurred when there are 2 data dependencies between instructions. And also in the control hazards occurs when there is a change in the program flow, like the branch not equal, jump, and other instructions. So if we go to the first structural hazard, so what happens is like if we pipeline these 4 instructions, the first one in this instruction and this instruction both use the memory instruction memory module at the same time. So the problem is like since both instructions are accessing at the same time, there will be a structural hazard. So to remove that structural hazard, what we can do is to implement a stalling scheme where we include a bubble in the pipeline and move the pipeline. We store or the delay the third instruction for 1 cycle, causing not to use the memory blocks at the same time. So it will reduce the stalling in the system. So in our system, we have implement a stored control unit. So Vihan will explain the stored control unit.
Thank you, Tarek. So let's look at the store control unit. So what happens in the store control unit is that we check whether the current address in the execution address, which is indicated as XRT. So that's the destination address of the execution address. Where we check whether if it is same as the instruction in the decoding phase, the registers, the source register or the target register in the instruction decoding phase. So in this implementation, so what happened is, so the data hazards occur like in the when source address and the destination address is same as the so in our implementation, so in load instructions and XOR instructions, the no data houses are occurring. So we exclude those two instructions by checking looking at opcodes and check with other instructions whether they are the current instruction destination register is equal to the decoding phase instructions source or destination registers. So let's go into the code of the component. So we check whether the two if two addresses are equal by uh, taking XOR between those two addresses we have received. So here we first check if the execution phase target register is same as the decode phase source register, and then we check whether the execution phase target register is same as the decode phase target register, and here we check whether the two instructions that I says that they are not be an data hazard is the load register and the XOR the instruction. So we check whether if it is performing this uh, the instructions. If it is not, we if it is not performing those two instructions, and if any of the above addresses are equal, we indicate it as if the condition has met true, and the condition is output as true to stall the uh, pipeline by one clock cycle. So let's move to the presentation again. So then we have control hazards in our pipeline where which is occurred by normally by branch instructions or jump instructions. So a simple prediction to avoid the that is normally taken by pipeline is that the branch is always taken, and the all instructions relevant to that instruction path is loaded into the pipeline. And if it is a correct prediction, there's no issue. But if there's a wrong prediction, then there will be a control hazard, and the only instruction that was loaded, assuming that like this branch will taken should have to be removed from the pipeline. So let's look at some examples on control hazards. So here we assume that this branch the instruction will take the branch, and we load the other instructions on that assumption, and actually it took the branch, and therefore we didn't have any uh, like a control set, so we can continue with the pipeline. But if you look at like a scenario where the branch is not taken, which is indicated shown in the next slide. So here we assume that branch will be taken, and we loaded the instructions to the pipeline, but actually the branch was not taken, and therefore a control hazard was occurred, and we had to remove all the instruction that was loaded into the pipeline, which is usually called as flushing the pipeline. So let's look at how this is handled in our implementation. So a separate block which is known as flush control unit, which will take input a signal flush, which will indicate if there's a need for a flush or not, and all the the signals that is relevant for the operation of those instructions. And if the flush bit is uh, high, we like make a zero all these signals that is taken into the flush control unit and output them as zero, make like removing all the instruction that was in the the pipeline. So if you look at the code of the flush control unit, so here, so what we do is we take the knot of the flush, and we and it take and we it with the inputs signals that we received as the instruction, the inputs that is relevant for the operation of the instructions. And if like if flush is 1, and the not flush will become 0, and the end anything that it is and it and with it will be equal to 0, and all the as a result all the signals that is relevant for the execution of the instruction will become 0, and the instruction will get flushed out from the pipeline. So let's go back to the presentation again. So next we have raw data hazards or read after write data hazards. That means like the next instruction should read the value from the register after writing the instruction from the previous instruction. So if it reads the instruction before the previous instruction writes for the register, there will be an erroneous calculation, and the program will not run as expected. To handle these kind of read after write data hazards, uh, we normally implement like a unit called forwarding unit, uh, and Taraka will explain the implementation of the forward unit in our implementation.
Thank you very much, Johan. So this is a typical example of data forwarding scenario. So what happened here is like we will have different register 32-bit elements connecting these 5 stages, and we will forward the value to previous calculations. As you can see in here, this instruction will produce the substructured result value in register 2, and it will be required in the AND operation. So what we will do is when this execution is completed, we will pass this value forwarding back up to this block. So from this block, we can easily read for the next instruction. So that will be implemented in a forwarding unit. In the forwarding unit, we will compare the previous addresses of the previous values with the next operations. So in the implementation, we will do a forwarding when 6 conditions are met. The first condition is the read write should be 1. That means it should be a write operation, and also the write register should be 0, and also the write register should be equal to the register source. So and also for the write back register should be write back write enable should be 1, and the write back write register should be 0, and also that value should be equal to the register target. So if all these conditions are met, we will do the forwarding as you can see in the code. The first we will have to make sure that the value is not 0. Then we will use the XOR operation to compare these 2 strings, the mem write rec and also the register source address, and also the same will be done. Same will be done for a write back and also the register source. Again, for this was discussed for the forwarding one part, the forwarding A. of the implementation. Then for the forwarding B of the implementation, we have to do the same operation, but this time it's with the register target vector value. So if these two values are equal and also the write register is not 0, and at the end we will check whether the register write whether the register write is set. If all these conditions are met, we will do the forwarding accordingly. So the next another hazard that could happen at the write back stage is writing and reading at the same address. So the readout data may not be correct writing data. To resolve the problem, we have created a write back forward unit to facilitate this address and directly correct writing data of the output address. So in here, we will input the data and also the address and also the data that should be written. And using these all four inputs, we will output what should be written out in our from this module. So if you go to the code of this implementation, it is same as the forwarding unit. The only difference is that we have a multiplexer to choose between what should be, whether we want to output the input read data one, this value, or the write data value. So what the write back forward unit is same as this previous forward unit. The only with the only difference of having a multiplexer which will allow us to choose between the write data or the read data, and output the requested value accordingly. So from that we can solve any issues that can be related to writing and reading at the same address. So this will conclude all the modules in our system. So in here, I have given a simple execution scenario that is implemented in our instruction memory. So at first, if I go through the what is given in instruction, first we will take the XOR immediate with 0 register, which is hard coded to the value 0 and the value 3, and we take the XOR and show it in the register 0. We do the same thing, register 0 and value 0, value 4, and we will XOR the value and store it in the first register. Then we will jump to next 3. I think this should be. From here, at the third instruction, we will execute the third. We will jump to the next 3 instructions. So as you can see, we have created an artificial scenario where we will have to flush these 3 values that is loaded to the program counter. So that jump was done to simulate this scenario. And from here we will do a subtract operation. We will subtract the value from the register 1, and we will subtract register 1 from register 0 and store the value in register 2. Then we will check the branch not equal. We will do the branch not equal operation, and we will compare the first 0th register and the first register, and if this is not equal, we will jump here, or else we will go from down here. So if the instruction is if the value from what we get here is not equal, we will again have to flush these values. If not, we can go ahead with the normal values. So we have implemented this here to check whether how the flush and also the data hazards are occurring in our system. So if I go through the normal instructions in the next stage, we'll have the store value and a load value, operations, and also less than value. Again, it's store our immediate values, and at the end, the jump register value. So this is our execution plan in our system, and this is what we are going to run and simulate in our whole MIPS processor. Next, let's simulate this operation in our MIPS processor. So the same instructions we have implemented in the instruction memory. So this is the instruction memory, and these 15 instruction corresponds to this shown instructions and in the same order. So let's run the simulation environment. So here, this is the output diagram of our algorithm of a processor. And if I go through the sum of the parameters, first we have the clock and the reset operation. So at first we will reset the whole processor so that all the register values will be set to 0. And here we have output the program counter, and I will set it to decimal value. And also then we have the opcode values here, the bus values of the arithmetic and logic unit. They will output the results of the arithmetic and logic unit. Then the instruction, the functions that's implementing, the register source value, register target value, register destination value, and also the important output from the control unit, which include the branch, jump, and also the flush output. So the explanation of this will be done by Vihan.
Thank you, Targa. So let's look at our program counter first. So as you can see, program counter jumps from increments by 4 by 4, indicating that our program is running instruction on instruction. And then you can see that after the executing of the 12th or the third instruction, it has jumped to the 20th instruction. That's because in our third instruction we have a jump to next 3 jump instruction. So but it loads the next instruction into the pipeline, which is the 12th instruction. And when jumping into the 20th instruction, the flush bit is uh, set to 1 and the loaded instruction is removed from the pipeline. That is, we can see that in our timing diagram where the flush bit has become 1 and the instruction has removed from the pipeline, and it will execute from the 20th instruction. So then again the instructions happens in order, and then after we have another branch not equal instruction in the next instruction. Uh, so we can see that in the timing diagram. Uh, so if we look at the corresponding values of the registers with these instructions, so after the first instruction, the register 0 is stores the value 3, and after the second instruction, register 1 stores the value 4, and then we have the jump instruction, so it will jump to the next one location, and there we have a subtraction instruction, so it will subtract um, it it will subtract the the 3 from 4 and store that value in the register 2, which is 1. And then in the next instruction, we have a branch if not equal instruction. So it will compare the two registers 0 and 1 and check the values in that. So 0 we have 3, and in the register 1 we have 4. So those are not equal, and therefore the branch if not equal is success, and it will jump back to the next to location, which is to the fourth instruction, or the in our case the 12th instruction location. So we can see that in our timing diagram. So here we after jumping to 20th instruction, then we keep executes that, and after executing for some time, we can see that after the 32th execution, we have jumped back into the and we can see that the flush has so after the branch not equal instruction, there should be some flushing of the pipeline, because some instruction has already taken into the pipeline, and those instructions should be removed from the pipeline, and then it will jump back to the 12th instruction, or in our case the fourth instruction, and then onwards it will execute the program again in the order, and then it will jump back to the next two location and take uh, the XO RI with RI means the XOR with the immediate value. So it will take the XORI with 1 and the 0 location is store 1 in the register 0. So register 0, it will store the 1 value 1, and then it will store the value. It will take XORI with the 0 and 3 and store the value 3 in the register 0. Uh, so when the jumping back to the next two instruction, it will take the XORI with 1 with 0 and store 1 in the register 0. And after that, it will take XOR with 0 and 1 and store that value in register 1. And then it will subtract uh, the register 2 and register 1 and register 0, and store that value in register 2. So then it will check the branch not equal instruction. So it will check the 0th instruction and the 0th register and the first register. So 0 register and the first register has the same value. So branch is not taken, and the process is continued. And then we have an add the instruction. So it will add 0th value in the 0th register address and the first register address, and store that in the third register. So it will add 1 and 1 and store 2 in the third register. And then we have stored instruction where we have s- so then in the stored instruction, we get the value in the register 2 and add it to the 16 and store that in the register 3. And likewise, the program continues to execute, and it ends by going back to the again to the start instruction, and the process continues to happen. So our timing diagram also goes as the clock is there, and all control hazards and data are handled in the meanwhile.
With that, the presentation of our project concludes. Thank you very much for joining with us.